The first homework was released yesterday. It's going to be due a week from yesterday, so you have 2 weeks to do it, essentially. It's a little bit shorter than a typical homework because you only have 2 weeks. Typical homeworks you have about 2.5 weeks. It's still not short by any means, so I would, we try to make them manageable, but I would start them as early as you can. So just take a look at it, if nothing else, this week. Pull it up and scan through it. And the office hour schedule's on the website. We have office hour, I think we have a total of 5 office hours per week, so if you're having trouble, you can try to come to one of those sessions. Last time I didn't get to do like a little demo with the quiz, so I was going to do that now to start us off. The first quiz isn't graded, so it was just up there for practice and to introduce you to the quiz system. The quizzes from now on are going to be graded, but as I mentioned, they're worth a very small part of your final grade. And the worst you can get is a 4 on the quiz out of 8, because even if you get the answer wrong, you can answer again as many times as you want until you get the answer right, in which case you get half credit. So there's 8 questions. The worst you can get is a 4. So I just wanted to demo the types of questions you're going to be asked so that people don't fret too much about the quizzes. This is going to be the quiz from the last lecture, so hopefully you guys haven't forgotten the contents of the last lecture by now, but we'll just go through a few of these. So true or false, if f is a convex function, then a valid constraint in a convex optimization problem is f of x equal to 0. You guys think that's true or false? False, right? Because the constraints have to be actually affine functions being set to equal to 0, right? So, all right, you got that right. Here's another one. So true or false, basically all algorithms for convex optimization perform the same across all problem instances. Picking an algorithm for a particular problem is mostly a matter of taste. True or false? OK, so I think we demonstrated that was false, right, with the example we had. So you can see the questions are both kind of factual like this one, and they're also going to be more or less an interpretation of what the lecture's message was. If we put true, you can see that the answer you're going to see is wrong, but then if we switch over to false, you'll get half credit. So the worst you can get, like I said on the quiz, is a 4 out of 8. So I don't know, let's just switch over to the last 2 questions. True or false, in a convex optimization problem, any local minimizer is automatically globally optimal. Is that true or false? True, right. That's what we proved at the end of the last lecture. And feasibility, if a point x is to be considered feasible with respect to a given optimization problem, which of the following need not be true about x? X is in the domain, D. So D is the intersection of domains of the functions that define the optimization problem. X minimizes the objective, F, or X satisfies the constraints of the optimization problem. So A, B, or C. Right. So again, if we picked C and it was wrong, and then we panicked and we picked A and that was wrong, then you can still go to B and you still get half credit. Oh, well, so now it says correct because it's in practice mode. But once the quizzes are out of practice mode, you'll see you get actually half credit for that. So, OK, that's the quizzes. Every lecture, like I said, we're going to upload the quiz right after lecture. It's due at midnight that night. So make sure that you remember to do that. The first few we'll probably send an announcement on Piazza reminding people like sometime in the afternoon or evening. After that, we're going to stop reminding you. So just get into the habit of taking them. Any questions about the quizzes? OK, any questions at all about the homework or any other administrative things? OK, let's jump ahead into lecture then. So this lecture and the next one are really going to be, I have to say, more dry than a typical lecture in this class because we're going to be covering the fundamentals. And while they are dry, they're extremely important. So we're going to be going through them pretty carefully. This is going to serve as the basis for understanding of everything that is to come. We're going to try to understand convex sets and functions very well today. And then next Tuesday, we're going to be understanding kind of the basics of convex optimization problems. Again, at a pretty fundamental level. If you find that there are certain things in this lecture that confuse you because you're rusty on one of the following topics, real analysis, calculus, or linear algebra, then we have some supplementary materials that are linked from the course webpage. So you can take a look at that. this lecture, the next one, pretty much everything from now on assumes that you're familiar with kind of basic real analysis, multivariable calculus, and linear algebra. So if you're rusty on those topics, then either come see us or take a look at those supplements. So last time, just to remind you what we did, we talked about convexity as a motivation for the course, and the main kind of motivating point was that convexity, the main point was that we can broadly understand and solve convex optimization problems. And we're going to see kind of the workflow of the classes that we're going to be talking about solving convex optimization problems for the first unit. It's going to be kind of like an algorithms unit. Then the understanding part is going to come afterwards in terms of optimality conditions for these convex problems. Non-convex problems we learned are treated mostly on a case-by-case basis. And as a reminder, the main thing that we learned last time was that if you have a convex optimization problem, which means something of this form, where the criterion f is convex, the inequality constraint functions are convex, and these equality constraint functions are affine, then it has the property that any local minimizer of this problem is automatically globally optimal. So we can't have isolated local minima. The outline for today, we're going to talk about convex sets, go through some examples of them, and some key properties of convex sets, and then we're going to basically do the same thing for convex functions. Just the same workflow, but for convex functions. So just a quick refresher, a convex set we learned last time is a set C that has the following property. Any 2 points in C, if you take the line segment that joins those 2 points, that line segment lies entirely within the set C. That's what this the mathematical implication of the statement is just that the line segment joining any 2 points lies inside the set. So that's something that I think most of you will be familiar with last time from a previous course, potentially. A convex combination is maybe something that you haven't heard that terminology, but certainly it's not necessarily a foreign concept. It just means taking a combination of points. So theta 1 x1 plus theta k xk. Here x1 through xk are, say, points in Euclidean space. Theta 1 through theta k are scalars. But a convex combination is a special linear combination where these weights here, theta 1 through theta k, are all non-negative, and they all add up to 1. Okay, so that's just what we mean when we say convex combination. So this is actually a convex combination of the points x and y, right? That's exactly what tx plus 1 minus ty is. The convex hull of a set is the space of all convex combinations of its elements. Okay, so just to define that a little more explicitly, if I give you a set C, the convex hull of the set, which we write as conv C, is the set of all points, we'll say theta 1, or so let's call it, say, theta I xi, I going from 1 through k, such that k is, just some integer bigger than or equal to 0. In fact, probably bigger than or equal to 1. It's the only way that makes sense. And x1 through xk are in C, and theta 1 through theta k are all non-negative, and they add up to 1. That's all we mean when we say convex combination. This is always convex. So no matter what set I give you, the convex hull of a set is going to be convex. So in this example here, with the kind of the bean-shaped set that we had, the convex hull of the set is going to look something like this. It's basically going to be this shaded area. So how can we see that the convex hull of a set is always convex? Well, first we can see, as an extension of this property, that this property is actually true for a convex combination of any number of elements of a set, right? Not necessarily just 2 elements. So a convex set is one that has the property that if I take a convex combination of any number of elements, that combination still lies in the set. Okay, you can actually see that by induction, basically, right? If I tell you it works for 2 points, and I give you a third point, then you can just kind of, by induction, determine that the convex combination of 3 points, which I can view as, basically 1 point plus the convex combination of the others, is also going to lie in the set. So this property holds true for any number of combinations of elements, convex combinations of elements. And that's exactly what the convex hull is, right? It's just a convex combination of elements. So by definition, really, the convex hull of a set is convex. OK, that's an important property. What are some examples of convex sets? So there's some really trivial ones, like the empty set is convex, right? Because we have to have this statement being true. For any x, y in the set C, the line segment joining them is in the set also. Well, there are no points in the empty set, so that is vacuously true, right? That implication is true. A point is convex because there's just one element of that set. So convex combinations just give you back that point. And a line is convex. A line is actually just this. It's given by this equation, but with t varying over all of R, for example, right? Not just between 0 and 1. A little more interesting ones are norm balls. So a norm ball is something of the form, the set of all x whose norm is less than or equal to r for some constant r. And we're going to denote an arbitrary norm by just double bars. So examples of norms are like the Euclidean norm, the L2 norm, the L1 norm, LP norms. There are also matrix norms that we're going to learn. So there's various different norms we could apply, but whatever the norm is, that's always going to be convex. So how do we see that one's convex? That might be just something we can do in our heads. If I give you 2 points that both satisfy the norm being less than or equal to r, just write it down. We'll just go through a few of these just for clarity. So if x and y both have the property that their norm is less than or equal to r, what is the norm of tx plus 1 minus ty? Well, we can use the triangle inequality, right? Any norm satisfies the triangle inequality. That's one of the defining properties of a norm. And it also has this property called positive homogeneity. All that means is that we can take out constants, right? It's just a fancy word for that. So I can apply both those properties and just conclude that this is true, right? And then this is less than or equal to r, and so is that. So the whole thing is less than or equal to r. So any norm ball is convex. A hyperplane is convex. That's the set of all x for which A transpose x is equal to b, where A is just a constant vector, and b is a constant scalar. Half spaces are convex. I get that from changing this equality to an inequality. Again, these you can see right from the definition. I'll leave those for you to check. An affine space is convex. So this is the solution set to a system of linear equations, ax equals b. Now, if A is full column rank, then that's only 1 point, right? There's only one solution to ax equals b. So that reduces to this trivial case. If A has columns that are degenerate in the sense they're not linearly independent, then that's actually it's a non-trivial subspace, but it's still convex. This one, again, you can check directly from the definition for a given matrix and vector b. Okay, so I'm just going to keep going. I'm probably going to even speed up a bit. So if something's not clear, make sure to interrupt me. I'm probably not always going to pause after each example. A polyhedron is convex. A polyhedron you get from changing the equal sign in a linear system of equations to a less than or equal to sign. And this we interpret component-wise. So everywhere from now on in the course, if we see a vector less than or equal to a vector, that means it has to be true for every component. So ax less than or equal to b means that every component of ax is less than or equal to the corresponding component of b. That's convex. Again, something we can see directly from the definition. This set is also a polyhedron, the set of all x for which ax is equal to b and ax is less than or equal to b and cx is equal to d. So you can represent a polyhedron in either way. So why is this also polyhedron? It's because we can take cx less than or equal to d and we can rewrite that as two sets of inequalities, cx less than or equal to d, and say minus cx is less than or equal to minus d, which is cx greater than or equal to d. And so we can stack that basically along the set of linear inequalities we already have, and so we can still see this as a polyhedron. Okay, so geometrically, this is important to keep in mind because polyhedra are very special, and we'll see them a lot in class, this is the intersection of a bunch of half spaces, right? How do you see that? So AX less than or equal to D is the same thing as AI transpose X. Don't know why I have D, I meant to say B. Is less than or equal to BI for all I, let's say, equals 1 through M, where M is the number of rows of the matrix A, and each row I'm denoting by AI. That's just really expressing that differently. Each one of these is a half space, right? We know that. And I'm requiring that basically X lie in the intersection of all of these half spaces. All of these inequalities have to be true. So this is just a picture of that. Basically, each one of the rows of A determines a half space, and I'm forcing X to lie on one basically side of that half space, and taking the intersection is giving me a polyhedron. A simplex is a very special polyhedron that has the property that it's given by the convex hull of, let's say, k plus 1 points, where those points are affinely independent. So the simplex that you'll think of and we'll probably just focus on for most of the course is the probability simplex, which is the convex hull of the standard basis vectors, E1 through En. So EI here is the vector that has all zeros except for 1 in the ith component. And the probability simplex is the set of all vectors, let's call it W, such that each component of W is non-negative and they add up to 1. Okay, so that's the probability simplex. Okay. Let's see. Who knows what affinely independent is? Is that a term that people haven't heard before or have heard before? Affine independence? Okay, so let's just be explicit about that. If I give you vectors x0 through xk, then we say that they're affine independent. If and only if I take, let's just say I pick one point like x0, that's why I denoted x0. If I look at all the vectors x1 minus x0 all the way through xk minus x0, these are linearly independent. Okay, so basically means that if I have a so linear independence basically means that if I take my points and I fit a subspace going through 0 through those points, then basically I can't have, let's say I have k points, I can't have more than one, that subspace can't be less than k dimensional. If I take the linear combination of all the points, basically I can't have the linear combination of, let's say, k of those points contain a k plus first point. That's what it means for a set of k plus 1 points to be linearly independent. Affine independence is basically the same idea, except we don't require that subspace to go through 0. Okay, so the subspace is allowed not to pass through 0. It can be offset by an arbitrary amount, and that's what this point x0 serves as the offset. So if we look at the differences of points, then those have to be linearly independent. That's, I guess, the way to think about it. So get comfortable with the idea of an affine combination or affine independence. It's something that will pop up here and there in the course. The Boyd and Vandenberg textbook has some supplementary material on that in the appendix, I think. Okay, cones are kind of an interesting cousin, let's say, to convex sets. Cones are sets that have the following property. If you give me a point in the set C, and C is a cone, then I require that Tx times C has to lie, Tx has to lie in the set C for all T that are non-negative. So I don't take a convex combination of points, I just take one point and I scale it. A convex cone is a cone that is also convex. So it has this property, and it has the property of being convex. So when you put those two properties together, what you'll see is that actually we require that for any 2 points, x1 and x2 in the set, if I take t1 times x1 and t2 times x2, then that has to lie in the set for all t1 and t2 that are non-negative. So we don't have to have them add up to 1, just be non-negative. That's what a convex cone, that's what's defined as a convex cone. So here's just a picture of that. Let's say this is x1, or this is x2, and this is x1. they're convex. Basically, well, I'm actually drawing here the conic combination of x1 and x2. Let me rephrase that. Let's suppose I look at this gray slab, and I ask, is it a cone, a convex cone? So I pick out any 2 points in the set, x1 and x2, and I take their linear combination t1x1 plus t2x2, and t1 and t2 are both allowed to be any non-negative numbers. That has to always lie in the set in order for that to be a convex cone. Well, you can just see that's true, right? If I scale x1, I get anything in this direction, it's still in the set. If I scale x2, I get anything in this direction, it's still in the set. But take any combination of the two they both have positive weights, it's going to lie somewhere in the middle. And if I scale by arbitrary amount, it's still going to lie in the set. Yeah, question?
Seems like every cone is a convex cone.
That's a good question. Is every cone a convex cone? How many people think that's true? Let's see. Raise of hands. OK, so everyone thinks it's not true. Can you give me a counterexample of a cone that's not a convex cone? What's that? One line? So one line is actually a convex cone, a segment. But you're very close. Just add one more thing.
It has negative part and positive part. Cone has the 0.
Yeah, so I think maybe you're saying something like this. If I just take 2 line segments and I join them together, that's a cone, right? Yeah, that's a cone. Right? Because if I take any point and I scale it by a positive amount, it's always going to lie in the set. But it's not going to be convex, clearly. So if I take combinations of these two, that doesn't lie in the set. So it's a good question, but cones can actually be a fair bit more intricate than convex cones. They can have some irregularities like that. A conic combination of points is just a linear combination of points where all the weights are non-negative. Okay, so just like we had the term convex sets, convex combinations, now we have conic sets and conic combinations. Again, all that means that I take any linear combination of points where the weights in that linear combination are non-negative. So actually, another way to interpret this figure is just to say this is the conic combination of x1 and x2. Okay, this is the space of all conic combinations of x1 and x2, and the space of all conic combinations of the elements of a set is called its conic hull. So this is all kind of analogous to the convex definitions just for cones. Some examples of convex cones. These are actually 3 examples that are fairly important. The norm cone is always a convex cone. So it's given by the set of all pairs, x and t, where x is a vector and t is a scalar, that have the property that the norm of x is less than or equal to t. So it's, if x is, let's say, n-dimensional, this norm cone is an Rn plus 1. And under the L2 norm, this is sometimes called the second order cone or the ice cream cone, or the Lorentz cone. For some reason, it has that name as well. So let's see if we can draw that in R3. So let's suppose this is x1 and x2, and this is the t-axis. What does the norm cone look like if I use the L2 norm in R3? It looks like the set of all vectors, x1, x2, and t, that have the property that the norm of x is less than or equal to t. So let's just take a slice, basically, of t. Let's suppose I take some slice. I have to maintain that the norm of x is actually less than or equal to whatever this value of t is. So it's everything within, let's say, that disk. And as t varies, I just get concentric disks. Okay, so everything that's in kind of, you can imagine taking 2 45-degree lines and spinning them around the t-axis. That is the second order cone in R3. Okay, so it's everything in here. Hopefully that drawing made sense to you guys. The normal cone is not the same thing as the norm cone, despite the fact that they sound really similar. The normal cone is a completely different object. It's also important. It is defined by a set C and a point X that's in C. So if you give me any set C, and any point x that's in the set, I can define the normal cone, excuse me, I'm mixing it up already, which I denote by n sub c of x. It's the set of all vectors g that have the following property. G transpose x is bigger than or equal to G transpose y for all their points y in the set C. So said in words, it's the set of all vectors whose inner product, if I take their inner product with every element in C, is maximized at x. So it has the biggest inner product at x compared to everywhere else in the set. So one very nice property of the normal cone is that this is always a convex set, regardless of what C was. C could be extremely non-convex, and the normal cone of C at any point is always going to be a convex set. So we're going to see a nice connection between that and subgradients later when we talk about subgradients. So this you can check directly from the definition. Again, I'll leave that maybe as something you can check offline. Let's just draw the normal cone at a few points of this set C to gain some intuition. Let's suppose I choose a point here. This is my point x. And we'll just, for clarity, let's have C contain 0. What's the normal cone of the set C at the point x? Right, so intuitively, I think this is the right intuition. We just think about it as the normal vector to x. Okay, but actually, we're actually translating that. That's why I drew 0 here. The normal cone is actually the set of all these vectors. It's the set of all vectors whose inner product with x, maximizes the inner product of that vector with all points over the set. But it just helps to think about translating that point to where x lies to visualize the normal to the set. Okay, so whenever we think about the normal cone, we'll think about if I were to take basically the point x and I take the inner product with this vector, but really this vector just shifted back down to 0. Let's draw 0 somewhere else so that it's a little bit more interesting. So you can convince yourself that if I were to take the inner product of x with this vector, I can't get a bigger quantity than that if I were to take the inner product of this vector with any other element of C. That's really the defining property of a normal vector, and that's what defines the normal cone. Okay, so think about basically scanning through the set and trying to take the inner product with this vector, and you can see it cannot be made bigger than it is with x. So this is the normal cone, anything that starts at 0 and goes off in this direction. So this is actually a one-dimensional cone. At some points, the normal cone can be actually more than one-dimensional. So if we're thinking about R2 here, what's the normal cone, say, at that point? This is another point. It's called x prime. You might convince yourself that it's anything that lies in between. Essentially, the normal at this point, if I think about being tangent to this part of the boundary, and to this part of the boundary. So it's anything that lies in between the conic combination of those 2 points, of those 2 vectors. So it's anything in here. This is the normal cone of C at the point x prime. Again, if I were to try to take the inner product of any of these vectors with x prime, they are biggest at x prime compared to if I take the inner product with anywhere else in the set C. Okay, so I think it'll help just to draw yourself a few pictures and go over the definition a few times. The normal cone is important because it relates to subgradients, which is very fundamental. We'll learn that later. Was there a question? Yeah.
Yeah, what's going on in the slide picture there? The 2 lines on top.
These guys? So I think it's just a little small. These are just demonstrating that this is the normal cone at 2 different points on the set, and this is the normal cone at that point on the set. What happens if I give you a point that's in the proper interior of the set C? What's its normal cone? What's the normal cone at that point? So suppose I pick a point that's properly within C, in its interior. What vectors have a maximal inner product with a point that's in the interior of the set C? Are there any vectors with that property? So if I picked something like here, right, the normal cone is just the point 0 itself. So the normal cone at this point would just be the trivial cone that contains 0 itself. So it's always defined. The last cone that we'll kind of deal with heavily in this class is the PSD cone, the positive semi-definite cone. This is the set of all symmetric matrices. So this means x in the script S superscript n, supposed to mimic the notation of Rn, is the set of all n by n matrices that are symmetric. And Sn plus is the set of all n by n symmetric matrices that also have the property that they're positive semi-definite, which we denote by x squiggly bigger than or equal to 0. So hopefully that's something that's still familiar to you. If you forget what that means, go look up the supplements for linear algebra. Just in one sentence, positive semi-definite means that all of the eigenvalues of that matrix are bigger than or equal to 0. Equivalently, it also means that if I take A transpose XA for any vector A, that thing always has to be bigger than or equal to 0. That's what it means for a matrix to be positive semi-definite. Some people, when they see this as an example, and when we start kind of going back in between matrices in Rn, they get kind of hung up on the fact that this doesn't seem like it fits the previous set of definitions that we made, because we're all of a sudden dealing with matrices rather than vectors. But it really does. So the way I would recommend thinking about the set of n by n symmetric matrices is that it's just a vector space where I've actually taken a vector of dimension n times n plus 1 over 2. The reason it's not n squared is because a symmetric matrix, right, it's only defined by n times n plus 1 over 2 entries, because the other half are completely determined. And I've just taken some vectors that are of length n times n plus 1 over 2, and I've actually just arranged them in a way that's nice for me to think about for matrices. But really everything else that we do is just treating that matrix like a vector of length n times n plus 1 over 2. We just overloaded certain operations like multiplication and other things like that. Okay, but it really is a vector space. So there shouldn't really be too much hang up when we start dealing with matrices and matrix norms and that kind of stuff when it comes to these definitions. Okay, so we've gone through the definition, we've gone through examples, the critical examples. What are some of the key properties of convex sets? There are two key properties of convex sets. To be honest, these properties are certainly fundamental, but they're not going to be properties that if you forget halfway through the course, you're going to be in trouble. I probably shouldn't say that now because it's not good motivation, but to be perfectly honest, you're going to be spending a lot more attention on convex functions and their properties than convex sets. Convex sets are important because really they're the building blocks for convex functions, but I wouldn't say that these two properties themselves are going to be critical to you being able to solve optimization problems. They're just important. So here they are, despite the fact that I kind of downplayed them. The first one is the separating hyperplane theorem. This says that if you give me any two convex sets and they're disjoint, so they don't have an intersection, then there exists a hyperplane that separates them. It means that there exists some set of the form A transpose x equals B, let's say for a vector A and a scalar B, such that one of my sets, call it C, lies completely in the set A transpose x less than or equal to B, that half space. And the other set, let's call it D, lies completely in the half space A transpose x bigger than or equal to B. That's the separating hyperplane theorem. It's clear that that's not possible if the sets weren't convex, right? So here's an example of two sets that are disjoint but non-convex. I certainly can't separate them by a hyperplane. That's a really important property of convex sets. The other really important property is the supporting hyperplane theorem. So it says that if you give me a convex set and you give me a boundary point of that convex set, then there exists a hyperplane passing through that point that supports the set. What that means, again, is that let's suppose the hyperplane is defined by A transpose x equals B, and this point is called x0. Then at this point I have A transpose x is equal to B, and on one side I have to have the convex set contained entirely. So the convex set, let's just say, for simplicity, has to satisfy A transpose x is less than or equal to B. That's what it means for the hyperplane to support the convex set. We get equality at the boundary point, and we get an inequality at all other points in the convex set. Again, that's not going to be true for arbitrary non-convex sets. You can draw yourself an example to see that. In a way, these are actually really almost defining properties of convex sets. So both of these statements have partial converses, which means that if I tell you, I give you a set at which every boundary point there exists a supporting hyperplane, then under some other conditions, that set must be convex. And same with the separating hyperplane theorem. There are kind of partial converses. So you have to just add a bit more conditions to get the converse. So they're really important properties of convex sets. OK, and the last kind of bit for our convex set segment is going to be operations that preserve convexity. So we saw examples, we saw key properties, we saw the definition, obviously, of convex sets. Now we're going to see operations that preserve convexity. So if I give you a set and I ask you, is it convex? At this point, all you can do is say, is it one of the examples I learned? Or can I check the definition and see if it holds? So unfortunately, that's not really a very useful kind of workflow, because the definition can often be very tedious to check. And I can only give you so many examples. So this is actually an extremely useful set of tools to remember. These are operations that preserve convexity. So we're going to learn something like, if you have a convex set and you do this operation to it, the result is always going to be convex. So you can bypass checking the definition for a bunch of different convex sets.
I have a question about the theorem support. Is any of those enough to say that a set is convex?
Almost. So they're almost enough. I'm going to not try to state the converse because I'm sure I'm going to leave something out. But if you go to section 2.5 of the textbook, then you'll see there are statements for each of these theorems that just say that if, let's choose the supporting hyperplane statement. If every boundary point of the convex set has a supporting hyperplane, so of the set has a supporting hyperplane, and I don't exactly know the other condition. Maybe it has to have a non-empty interior or something, like some other not very strict condition. Then the set must be convex. So they're not full converses, but they're partial ones.
Is it possible for one point in the set to have more than one supporting hyperplanes? Looks like in that case,
more than one supporting hyperplane. Yeah, sure. So let's see if we can. OK, yeah, in this example, which points have more than one supporting hyperplane? These corner points, yeah, right. I can choose different supporting hyperplanes. So we're going to see, actually, there's a very neat connection between this and subgradients. But that'll come a little bit later. Good questions. OK, so let me tell you about these operations. There's a bunch of pretty basic ones, and then there's some ones that are pretty useful. Intersection, I can take the intersection of any number of sets, and it's always convex. That's very easy to check from the definition. So you can, once you convince yourself of that once, you can intersect as many sets as you want that are convex, and you'll always get a convex set. That's even true for an infinite number of sets you're intersecting, even if that number is uncountable. It doesn't have to be even like an ordered sequence. Scaling and translation. So if I give you a set C, and I take that set and I multiply it by a constant A, and I add a vector B to it. So that's this notation is A times the set plus B. That means the set of all A times X plus B, where X is in the set C. That's always convex, as long as C was convex to begin with. That's important. The last one I'm going to share, just because, like I said, we don't really deal too much with convex sets. We'll see a lot more for convex functions, are affine images and pre-images. And this one is actually very powerful. It's very important. If you have a function that's an affine function, again, remember, that's just a weird term that we use for linear functions that have an offset. So f of x is equal to a times x plus b, where a is a matrix and b is a vector. Then if I give you a convex set C and I apply that function, I take the image of that set under the function. I note that by f of C. So that's the set of all f of x such that x is in C. So I'm taking every element of C in this case, and I'm multiplying it by the matrix A, and I'm adding B to it. If C was convex, then the affine image of C is always going to be convex. Again, something that's very useful, and you can check right from the definition. So this is more than a scaling in a translation, right? So adding B is a translation, but multiplying by a matrix A does a lot more than scaling. It can be a rotation, it can be a dimension reduction, it can do a lot more with a linear transformation than just scaling. And importantly, the inverse image of any convex set under an affine function is always convex. So this notation, if I say I'm looking at f inverse of a set D, that doesn't mean that the function f has an inverse. Doesn't mean that there is an inverse function to f. It's just notation that reflects the set of all x such that f of x is in D. Okay, so it's very important we don't confuse that with the inverse of the function. It's just the way it's written, unfortunately. So, for example, if A is non-invertible, and let's say it goes from Rn to Rk, and k is a lot smaller than n, then this is still well-defined. It just means the set of all points such that if I had applied the function to that point, it would have lied in the set D. Okay, so it's called the inverse image or the pre-image. Again, if D is convex and f is an affine function, the affine pre-image of D is always convex. Okay, so that's a very useful last set of facts. So let's just take an example of that. We're going to look at what's called a linear matrix inequality solution set. So that's the set of all vectors x1 with components x1 through xk that satisfies the following inequality, and it's actually a linear matrix inequality. It looks like this. If I just take x1, that's just a scalar, right, times some matrix a1 plus x2, a2 all the way through xk, ak, where a1 through ak are fixed symmetric matrices. That has to be less than or equal to, in the matrix sense, another fixed matrix B. So what does that mean? Remember we said that this notation means that B minus x1, a1 plus xk, ak is bigger than or equal to 0. In other words, that means it's positive semi-definite. So this matrix is positive semi-definite. Okay, so with respect to this inequality, a1 through ak and b are just matrices. They're just fixed matrices. And x is the variable. So I'm interested in the set of all x that satisfy this. So the set of all x such that this inequality is true. You can maybe convince yourself this is like a matrix version of a polyhedron, right? I don't have vectors here, I actually have matrices. I claim that's a convex set. And what's kind of remarkable is that's true even if without conditions on a1 through ak and on b. These have to be symmetric, but they don't have to themselves be PSD. That's always going to be a convex set, no matter what I put here. So there's two approaches to that, to proving that set's convex. Let's just go through that so we can demonstrate the two ways to do it. The first is just to directly verify that it's convex from the definition. So right, if I take any points x, y in this set, I have to prove that their convex combination is in this set. So let's suppose I have a point x that satisfies this. I'll call this C. And I also have a point y that satisfies that. And now let me look at tx plus 1 minus ty. I want to prove that basically this matrix, if I replace x with that convex combination, is still PSD. Right? So I want to take, let's just call z tx plus 1 minus ty. To check that z is in the set C, I want to prove that this matrix is still PSD. So probably the easiest way to do that is actually just to, again, recall the direct definition of what it means to be positive semi-definite, and one of the equivalences is that if I take any vector, let's call it A, and I take A transpose this matrix times A, that's still bigger than or equal to 0. So I want this to be true for any vector A. Right? And now I'm going to expand out Z, and remember that it was equal to Tx plus 1 minus Ty. And so I'm basically going to get A times B minus x1, A1 minus xk, ak times A times T. So I just pulled out the T from all the terms involving x, plus 1 minus T times A transpose, the same thing but involving y. And because x is in the set, this is always going to be bigger than or equal to 0 for any A. Because y is in the set, that's always going to be bigger than or equal to 0 for any A. So I have T times something non-negative plus 1 minus T times something non-negative. And that's bigger than or equal to 0. So I've just checked from the definition that I have convexity based on the definition. Okay, so that was one way to do it. It was somewhat tedious. Yeah?
Yeah, how do you know that the sum of two positive semi-definite matrices is also positive semi-definite?
Sorry, which step?
It seems like, yeah, the last step.
This?
It seems like you're assuming that the sum of two positive semi-definite matrices is also positive.
Uh-huh. So that you can see that from the definition in terms of like taking A transpose. So to be positive semi-definite means for matrix M means that A transpose MA is always bigger than or equal to 0 for all vectors A. So I've just actually done that, but I've expanded out A transpose the first matrix times A plus A transpose the second matrix times A. So I've just split it up into two separate terms. That's the way to see it. OK, that's approach 1. Approach 2 I prefer because it's shorter, and hopefully be something that you guys adopt as well. Second approach is to recognize that this looks like the positive semi-definite cone. The positive semi-definite cone, we already learned, is a convex cone. It's a set of all matrices X such that X is PSD. OK, that's convex. We know that for a fact. Let's call that D. And now I'm going to look at this and I'm going to say, well, I'm actually applying a linear transformation here, basically, and just rearranging for this inequality. So I'm going to define, I have it on the slides here, a function that goes from Rk to the set of symmetric matrices that are n by n to be the following function. Give me B minus the sum of xi ai. And I can see actually directly that this set, C, the set of all x's that satisfy this matrix inequality, is just the inverse image of the positive semi-definite cone under this affine transformation F that I defined. Okay, so it's the set of all vectors for which, if I were to apply F to them, then this would be positive semi-definite. And this being positive semi-definite rearranged is really just this inequality. Okay, so it's just two steps there. Convex cone of positive semi-definite matrices and an affine preimage, and I didn't have to check anything. Okay, so a lot shorter. I'm going to skip this example just because we're probably going to come back to it at some point. Another nice example that relates to PCA, but I'm going to skip it for now, just because we're a little bit short on time. A couple more operations that preserve convexity. I'll just mention them so that you know what they are. If you take any perspective images and pre-images, then that always preserves convexity. So a perspective function is a function that applies to a vector and then a scalar. The scalar has to be positive, and it gives you back the vector divided by the scalar. So it goes from Rn cross R++. R++ means all the strictly positive reals to Rn. And if you pass it, let's say x comma z, where x is the vector and z is positive, gives you back x over z. That always preserves convexity. So that ends up actually being important in some applications. And its inverse image also preserves convexity. I'm not going to give well, there's an example of that in the slides of how you use that, but for the sake of time, we're just going to kind of gloss through that. And lastly, the most kind of general version of this is what we call a linear fractional image and preimage. And that's the perspective function composed with a linear transformation or an affine transformation. So I take in a vector x, and I give you back ax plus b over c transpose x plus d. So I apply an affine transformation to give you back a vector, and then a one-dimensional affine transformation to give you back the scalar by which to divide. And the domain of this actually requires that this be positive. C transpose x plus d be positive. It also turns out that if you take any linear fractional image of a convex set, so anything of this form applied to a convex set, or a preimage, then you always get a convex set. Okay? We're not going to really run into that too often, but I wanted to put that down. And there's a nice example on the next slide. OK, so that was it for our convex set, like little segment. Are there any questions about convex sets before I move on to convex functions? No? OK, let's take a short break, maybe like a few minute break, 2-3 minute break, and then we'll come back and do convex.